Here's a video on measuring particle size distributions of nanoparticles the MicroTrack-MRB way. Laser amplified detection, power spectrum data analysis, solid state probe optical bench, option for in situ measurement. The agenda: basics of MicroTrack DLS analyzers, quick review of Brownian motion, an optical fiber coupler detection technology with laser amplified detection, power spectrum data analysis. We'll go over some measurement results and summary. Dynamic light scattering, DLS, measures the size distribution of particles in the nanometer range 1 to 1000 nanometers by general definition. However, DLS analyzers these days can measure below 1 nanometer and up to as high as 10,000 nanometers. DLS measures the velocity distributions of nanoparticles under Brownian motion and calculates their size distribution. Smaller particles have higher velocities than do larger particles. The MicroTrack-MRB dynamic light scattering features laser amplified detection for the strongest optical signal in the industry. Direct power spectrum analysis, no autocorrelation needed, and a solid state optical probe for in situ analysis. This is the DLS product line. We have the NanoTrack Wave 2, the NanoTrack Wave 2Q, and the NanoTrack Flex. The NanoTrack Wave 2Q measures zeta potential, molecular weight, and concentration in addition to size distribution. The 2Q measures molecular weight and concentration in addition to size distribution. The Wave 2 is different from the Wave 2Q in that it has a permanent measurement cell, and the 2Q measures samples in cuvettes. The next product is the NanoTrack Flex, where we have the optical bench probe outside the instrument connected back through fiber optic cable for in situ measurement, which is what's taking place right here. Quick review of Brownian motion. It's the random velocity and direction of particles or droplets suspended in a medium. The pattern of motion consists of random fluctuations of their position inside the medium, maintained by the collisions from the molecules of the medium. And here we show droplets or particles in red traces, called a random walk, from the sequential collisions of medium molecules. Brownian motion again, the random velocity distributions of particles suspended in a medium caused by collisions from molecules in the medium. Smaller particles have higher rates of change of velocities than do larger ones. And here we have an example of larger particles and smaller particles, and the velocity distribution of the larger particles lower than the velocity distribution of the smaller particles. This is an artist's conception of our optical probe, and it's missing a key point here, and that's the laser reference beam shown right here. This is my artist's rendition of our optical probe. We have the optical bench probe here in a steel casing. We have a lens focusing the laser beam directly onto a small volume of sample right at the interface of the probe tip. And at the end is a reflecting sapphire window with a very high reflectivity, and it reflects a portion of the laser beam back to this detector. The laser reference beam has a very high optical signal. It also enters the sample, and from the sample volume right here we get the raw sample scatter, which has a low optical signal. But when that signal goes back to that same detector, the scatter signal mixes with the laser reference beam, and the high optical signal of the laser reference beam is added to the scatter signal so that we detect a very high optical scatter signal. This incidentally is the first DLS method commercialized in 1990 to measure low through high concentration samples, anywhere from 400 parts per billion to 40% weight by volume. Laser amplified detection using the controlled laser reference beam. Controlled laser reference method of amplifying the sample scatter signal provides hundreds to millions of times the optical signal strength of the raw backscatter signal as used in other methods. This is a function of scattering efficiency of the particles, the size distribution, the concentration, and the relative refractive index. The advantage increases as the particle size gets finer and scattered light decreases, resulting in higher sensitivity and accuracy. This is a photo of the NanoTrack solid-state optical bench probe. It's only 4 inches long, and it can conveniently fit into many different size vials of samples, which means that the probe can be inserted for in situ analysis and no shearing of the sample from pipette transfer. Power spectrum data analysis, the MRB way for DLS analysis. Here we have the representation of larger particles and smaller particles in suspension, larger particles with lower velocities, smaller particles with higher velocities. And this is where we have the high optical signal from the laser amplification of the scatter signal. We perform a Fourier transform on that data, and we get a linear frequency power spectrum. And here it's represented with a 6 nanometer, a 60 nanometer, and a 600 nanometer particle, and where they would plot on a linear frequency power spectrum. We have amplitude and frequency increasing in the x-axis. We convert the linear frequency power spectrum to a log frequency power spectrum, and now we show definite modes at 6 nanometers, 60 nanometers, and 600 nanometers. Other methods that use autocorrelators and no controlled reference operate on the low optical signal that's generated at the point of measurement. Here we're showing a bimodal size distribution plotted in the logarithmic power spectrum. We have a 15 nanometer particle and a 120 nanometer particle. When we deconvolve this power spectrum measurement, we come up with the standard log normal size distribution. And we show the x-axis with size increasing to the right. And here we have our mode of the 0.01 micron particle distribution and the 0.1 micron particle distribution. This just shows the operations that preceded getting into the power spectrum measurement mode. Here we have examples of MRB DLS measurement reports. This is the summary report, and it provides all the information you need to know about one measurement. We have tabular data over here with sizes in this column, percent in each size, and cumulative percent. We have the graph in this corner of the report. We have the summary data and the percentiles down here. We have all the measurement information and all the information that you need to know about the standard operating procedure that was used. Up here we have another report showing a bimodal distribution of liposomes, and we have a mode down here at 7 nanometers, which is where the laser amplified detection is at its best, and we have a mode up here at 70 nanometers. Here's another representation of a measurement where we're showing the measurement of 2 different inks for inkjet printers. We have a magenta distribution here, which starts at 30 nanometers, and we have a distinctly bimodal distribution of the blue ink, which goes up to 2800 nanometers. And that's a nice broad dynamic range. In summary, NanoTrack's unique in situ capability can be used to make measurements in the many types of chambers for immediate sequential results of measurements on the same sample, avoiding sample transfer. A controlled laser reference beam provides laser amplified detection for up to millions of times the optical signal and signal-to-noise ratio compared to analysis by other methods which use no reference signal. Measure high through low concentration samples, all at 180-degree angle in one measurement. No need for multiple measurements at different angles. And velocity distributions are transformed direct to power spectra and deconvolved to size distribution. No need for autocorrelation.